Hey, welcome guys. Yeah, so hopefully subscribe to my channel. So in this video, let's keep talking about the series. Okay, a series or a sequence should be sequence. Okay, sorry, I'm stupid. Okay, so previously that we just talking about the Cauchy sequence, and also we talk about converge implies the sequence is Cauchy. If in the compact space, that Cauchy implies the convergence. And then we define a so-called complete if every Cauchy sequence is converged. Okay. So in this definition, in this contents, that we talk about special results. Okay. So what we are saying is that converge implies Cauchy, and but Cauchy need not to be converged, right? So, but in their case that in a special case there's a thing called monotone. Okay. So let's define the monotone. So sequence, very easy definition. So sequence Sn is said to be monotone if this monotone, this is called a monotone increasing, and this is called a monotone decreasing. Okay. Okay, so theorem, which is very important, is that if n is monotone, okay, so let's say an is increasing, so I use this arrow means increasing, and the boundary above. So that means an, you see, so yeah, so let's say this is n, right? So your an will increasing, but there's a bound here. Okay, so imagine so there should be you should hit some points, right? And cannot keep increasing. Okay, so your intuition is correct. Then an converge. Okay, also b if an is decreasing and the boundary below. So that means there is a bound such that an greater or equal to something, then an converge. Okay, so this is called the monotone convergence theorem. Okay, so monotone convergence theorem. Okay, quickly see a proof. I think I only prove A, right? Because if you times minus sign, then you get B. Okay, so we only prove A. Yeah, so should be very easy that E to be a range of, so that E to be a set of this, let's say AN, right? So from 1 to 2 to 3, to 3 and keep it to infinity. I let this is E, right? View as a set. Okay, so so since AN is bounded, let's say bounded above. So what? So we should have this E, right? So E will have suprema, right? So suprema, because this is bounded, right? So E is a set which is bounded by some n, right? For m is that means the upper bound, right? You have a bound, so you will have suprema, right? So suprema E will be finite. Okay, so from this so by definition, right? So it means that for epsilon greater than 0, you can find n, right? You can find there exists n belongs to n such that this an will less than suprema of E, but greater than the suprema of E minus epsilon, right? This is definition to be the suprema. Okay, so what we have is that the suprema E minus epsilon less than or equal to an and the suprema E, right? But an is increasing, right? An is increasing for all n. So actually, this sentence just tell you that an minus suprema E, let's say ax minus suprema E less than equals epsilon for all x greater than n, right? So by definition, this is just saying that for all epsilon greater than 0, you can find a positive integer such that when x greater than to the positive integer x minus suprema E is less than epsilon. So which tell you that an converge. Okay, and to what? To suprema. Okay, so to do another case, you just change suprema to be infinity. Okay. Okay, so we prove it. Okay, let's talk about another idea called the upper limit, and the lower limit. Sometimes people do not talk about this, but I think this is important, so I want to talk about. Okay, so let's definition. So let's quickly say a special definition. So if let's say for all m greater than 0, there exists n such that when an greater than m, then we write an converge to infinity plus infinity. Okay, so this means that you take actually this greater or equal to 0 is not important. So basically for any m becomes that in a real number, if you have any m become it's a real number, and then you can find n such that when n greater than m, such that for every n, I should say for every large n greater than this small n, this an will larger than m, means then this I denoted an converge to infinity. So same definition is that if for any m, if there exists n such that when larger n greater than small n, your an less than m. So that means n can be arbitrarily small, right? So I write an converges to minus infinity. Okay, so now we can define upper limit and lower limit. Okay. Right, so suppose you have Sn, which is a real complex, and I can denote the set E. This E is can be this E, right? This E defined to be all the points X, which X is converge. Points converge point of subsequence. Okay, so what I'm saying is that you take of subsequence Sn. So basically you take some subsequence and you convert. Once you converge, you take this XX and collect it. Okay, so by our definition, so E can allow infinity or minus infinity. Okay, so for example, if you take your Sn to be, let's say 1 minus 1, 1 minus 1, right? This will not converge, right? Because by definition, this will not converge. But you can take a subsequence of is 1, right? And then you can take take the even number, then it become another convergent sequence. So this E in this case will be minus 1 and plus 1 and minus 1. Okay. Or for example, if you have E like E2, E3, E4, E5, right? This is sequence. And then you can see your E. If I pick this, then this converge to 1. If I pick 2, 3, 4, 5, then converge to infinity. Okay. So basically, it's all the converge point that you can get, and from all the subsequence. Okay. And I think I proved previous time that the E will be closed. Is closed. Okay, but now we can define a so-called upper limit of S defined with suprema of E, and the lower limit called the infinity of E. This is just definition. So this is the definition. This is called upper limit, and this is called lower limit. Okay. Yes. Okay. Okay. And then there's a notation that people like to use called the limit soup. So this is a stupid, I think the hard, a very strange notation. This is called the limit soup, and this is called infinite. The lower limit is defined called the limit inf. So limit inf Sn. So this is just the upper limits and the lower limit. Okay. So this is the limit inf and the limit soup. Okay. And then there's the property of it. But I think it's a little bit long, so I don't want to prove. Okay. So there's some exercise you can try. Okay. Okay, that's just some examples. Right, so suppose you Sn to be the sequence contents or rationals. So remember rationals is countable, right? So I can define a sequence itself to be rationals. Then your limit soup. right, can be infinity, right? And then your limit inf can be negative infinity. So let's say b is Sn is minus 1 to n, 1 plus 1 over n, right? So your limit sup. So limit sup is what? Limit sup is the limit sup from here. You can, if you choose all the plus sign, right? This is 1, and the n goes to infinity, this is 1, right? And the limit inf is minus 1. Okay. Okay, and also a theorem, which is I don't want to prove, but it's very easy. Suppose your limit Sn converge to S, right? That means every subsequence converge to S, right? You can easily prove that it means that every subsequence converge to S, right? So easy to see that if the limit sup and the limit inf converge to S. Okay, so proof is just exercise. I think this is a simple exercise. Yeah, just from definition. Okay, so I think this direction is trivial, right? Because each converge, and then you can prove that if limit sup and inf are all the same S, means that every convergent sequence converge to S, and you can change to every subsequence converge to S, change it back to your original one. Yeah, I mean this is the same as this, right? Because if every subsequence converge to S, then this sequence converge to S. Because I can choose a subsequence to be original sequence S, right? So almost trivial. Okay. Yeah, and also some theorem which should be various exercise. I think this is easy, so I don't want to prove. Yeah, so this is 0, right? If p greater than 0, and also limit is n goes to infinity is 0. Sorry, it's 1 as p greater than 0. Also, maybe c is this. Okay, so n goes to infinity is 1. Yeah, you can use la Pitot to do this, I think. Yeah, I mean, this is all similar. Okay, also limit x and is 0. If x is less than 1. Yeah, these are all trivial, so I don't want to spend time proving an example. So all my video just want to highlight the technical stuff. I mean, up to now it's still not technical. Okay, so next time we talk about series, and the key for this the key for this section is that I want to prove the famous ratio test and also integral test. I want to prove this, and I want to prove why this theory will work, but not just using it. So alternative test, and also like a various root test. Yeah, so I want to focus on the proof. So I want to focus on the proof. A proof of this method, of these methods. Okay, and not the examples. Okay, so yeah, this is for the series part. Hope to see you guys next videos. Subscribe to my channel. Bye bye.